So concepts like percent yield become important in industry. If you're making large amounts of fertilizer or something, you're going to care a great deal about your percent yield. And you're going to want to know which is the limiting reactant and which are the excess reactant. And so what they'll typically do to minimize waste is they'll make the limiting reactant the one that's more expensive, so they can be sure that they use all of that up, and the less expensive reactants will be the excess ones. When we're working in the lab, we don't measure things out in moles. We measure things in grams. And so we can do mass-to-mass stoichiometry calculations with this concept of limiting reactant. And it's very much like what we did last week earlier in the chapter. We just have to add 2 steps to the calculation. So let's do an example of this. Suppose we have 53.2 grams or grams of, good grief, grams of sodium and 65.8 grams of chlorine. What's the limiting reactant and theoretical yield for this reaction? Well, 53.2 grams of sodium, write that under sodium in the balanced chemical equation, and 65.8 grams of chlorine, we'll write that underneath. They're asking us for the theoretical yield. We only have one product here. Sometimes there's more than one product, and the question should tell you which one they're interested in. But here, since there's only one, they don't need to say that. Question mark. And again, this problem doesn't specify the unit. It's safe to assume that we should find the mass in grams. So we look at this, and we have a mass of one reactant and a mass of another reactant. And we need the mass of product. 2 reactants here with 2 masses means 2 calculations. And here we're going to go back to grams to moles to moles to grams. Here we're starting with grams and ending with grams. And so we need to do the whole thing. The previous 2 examples were mole to mole, and we just did this part in the middle. And we didn't have to mess with grams on the end. Usually we do have to mess with the grams. So we'll start out with grams of sodium, 53.2 grams of sodium. We'll go grams of sodium to moles of sodium. Grams to moles, and then we go to moles of the product, moles of sodium chloride. So we've got grams to moles, and now we need to go to grams. So this last one will be grams of sodium chloride. Grams to moles to moles to grams. It's never moles to grams to grams to moles. You can't turn it inside out. It doesn't work. Grams to moles to moles to grams. So then we get our units in. So those cancel. And these cancel. And then we've got moles of sodium chloride down here. And now we need numbers. The middle term is the easy one. The numbers here come from the balanced chemical equation. We have moles of NaCl, so we find that in the equation. It's got a coefficient of 2. It's going to have a 2. And sodium has a coefficient of 2. We've got sodium down here in the bottom, and so that needs a 2. The first term and the last term are molar masses, and we need the periodic table. So we find sodium on the periodic table, and it says 22.99. And then this is a compound, and so we need the molar mass for that. I'm going to sneak it up here in the corner. We've got sodium. There's one sodium in there, and there's one chlorine. I think it's 58.44. 58.4. Oh, darn it. 58.44. That's the mass of 1 mole. So 1 mole is 58.44. Now we get out our calculator. 53.2 divided by 22.99 times 2 divided by 2 times 58.44. 135. Sorry, that's kind of small. .23 grams of sodium chloride. We're not done with the problem, so I'm not going to round it yet. But this had 3 significant figures. 4, infinite, 4, and so this will have 3. And so while I was thinking about it, I underlined the 3rd digit so that I wouldn't have to think about it again later. Okay, I'm going to switch to a different color so that we don't run these together. So that was the sodium. Now we need to take the other reactant and do a similar calculation, calculate how much product we can make if we could use all of that up. It gets a little tedious. Life can be tedious. I wish it could all be, roller coasters and stuff, but we might get tired of that. I think excitement is actually overrated. My opinion. So grams to moles to moles to grams. So this time it's grams of chlorine to moles of chlorine. We're going to the same ending point though. I need moles of sodium chloride and grams of sodium chloride. And then I put my units in so that they cancel out. Those guys cancel. Moles of chlorine cancels. I actually like this really cheapy stylus better than that super expensive one my husband bought for me. Don't tell anybody. He never watches my YouTube channel. Okay, got all the units in. The middle one I like to start with because it's easy. In front of sodium chloride is a 2, so I write that in here. And in front of chlorine is nothing. It's an implied 1, so we put a 1 there. Now, look what happens here. Grams of sodium chloride per mole sodium chloride, grams of sodium chloride per mole sodium chloride. That's the same, isn't it? It should be the same. Well, we don't have to calculate that again because we already did. We can just copy it down. 58.44. And then we have to go back and pick up this guy. That's 2 times the mass of chlorine, which I believe is 70.9. 70.90 grams of chlorine. And then we get out our calculators. 65.8 divided by 70.9 times 2 times 58.44. And here we get 108.47. Again, with 3 significant figures. Grams of sodium chloride. Then you ask yourself, which of those answers is smaller? Well, the 108, right? So this is our theoretical yield. Well, let's neaten that up a little bit and round it off. Theoretical yield equals, That's going to be 108 grams with 3 significant figures. And what's the limiting reactant? This is our smallest yield, our theoretical yield. We come backwards and it's the chlorine. Limiting reactant is Cl2. Any questions? Yes?
Clarification question. For the mass of the chlorine, you multiply by 2, that how much? Right?
Yes. I multiplied the molar mass of chlorine by 2 because the formula here is Cl2. In this reaction, chlorine is an element by itself. And so its formula is Cl2, and when I calculate the molar mass of it, I have to include the 2. Now, chlorine is in sodium chloride over here. There's no 2 on it. So I'm not going to throw an extra 2 in there. The other thing I'm not going to do is I'm not going to multiply, I'm not going to involve the coefficient in any of my molar mass calculations. Okay? We need 1 mole. The 2 comes in the mole ratio. If you try to put it in other places as well, you're going to get confused. It's going to get ugly. There was something else I was thinking of. Oh yeah, I'm just thinking that, chlorine atoms are like junior high girls. They don't like to go to the bathroom alone. They don't like to go to McDonald's by themselves, right? So they'll go with each other. But here, chlorine is not alone. She's with sodium. So she's completely happy to be with sodium. She doesn't need a girlfriend with her when she's out with sodium. Okay? So the diatomic thing is only when those 7 elements are alone. Okay? Any other questions? Let's do another example. Ammonia can be synthesized by this reaction. What's the maximum amount of ammonia in grams that can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen?
We're going to be really quiet.
Okay. That's fine. Okay, you two people. People are painting the outside of my classroom door during class. It's fabulous. Okay. Now, this question doesn't say anything about limiting reactant, doesn't say anything about theoretical yield. Oh, does it? It doesn't. Well, we have an equation here, and we have some masses, so let's just use this equation to organize the numbers, and then maybe we'll figure out what exactly it is that we need to do. Sometimes when you're doing one of these word problems, what you need to do is not immediately obvious. You can still start. Put down what you do know, and then puzzle on it for a while. Don't give up too quickly. So we have a mass of nitrogen. Well, I'm going to write that up here. 25.2 grams. 25.2 grams of that. And I've got a mass of hydrogen, 8.42 grams of hydrogen. And they're asking for maximum amount of ammonia in grams. Well, this is ammonia. They want to know how many grams. So, question mark, how many grams? Now we look at this. We've pulled all the information out of that question. We have 2 reactants. We have masses of both of them. That's the big clue that this is a limiting reactant problem, even though it doesn't say limiting reactant in the question itself. So what I need to do is I need to take the mass of hydrogen and figure out the mass of ammonia that can be made. I need to take the mass of nitrogen separately and figure out the mass of ammonia that can be made. 2 calculations. So I'm going to start with hydrogen. You can start with the nitrogen. I just like to start with the first one first. You can be different and do the other one first. 8.42 grams of hydrogen. Grams to moles to moles to grams. So first I need to convert from grams of hydrogen to moles of hydrogen. Then I'm going to convert to moles of the product that I want to find. And then I'm going to go to grams of that product. Grams to moles to moles to grams. Put the units down here. Make sure that they cancel out the way they're supposed to. And then moles of ammonia down here. One thing. Middle one's the easy one. Here's NH3. I find it in the equation. It's got a 2 in front of it. So I put a 2. Okay. Moles of hydrogen. Hydrogen has a 3 in front of it. I put a 3 there. Now, I think this one's the next easiest. Grams and moles, that relationship, you always need the periodic table. So that one, I'm going to do this at the top because there's just not enough space on these slides. H2, so I find H on the periodic table, 1.008. H2 I have to multiply by 2, and so I get 2.016. And that, I haven't been doing this, but that's grams is equal to 1 mole of hydrogen. So then here I put 1 mole and 2.016 grams. And then we need to find the molar mass of the ammonia. So ammonia is 1 nitrogen, 14.01, and 3 hydrogens. And I believe that comes out to be 17.034 grams is equal to 1 mole of ammonia. Check me on that. So that's the number that I need for this term. It's always, with these molar masses, it's always 1 mole, and the number goes with the grams. So 17.034, 1 mole. So now I multiply and divide across. 8.42 times 1 divided by 2.016 times 2 divided by 3 times 17.034 divided by 1. And I get 47.429 grams. Because I started with 3 significant figures and everything along here had 3 or more, this will have 3 sig figs. Now what do I need to do? I need to do another one. I need to start with the nitrogen and find the mass of ammonia. Where's my blue? There's blue. Oh, I forgot what class I'm in. I'm supposed to be using red, not orange. Orange goes with the other slides. Sorry for the color clashing. 25.2 grams of nitrogen. Grams to moles to moles to grams. So there's my grams. And then I go to moles of nitrogen. And I'm still trying to find moles of ammonia. I'm going the same way here. And then grams of ammonia. Put all the units in so they cancel out. I got all my units in place. The middle one, from the equation again, in front of NH3 is a 2. So I've got 2. And in front of nitrogen is nothing. So that's a 1. My last term is the same. So I'm just going to put that same molar mass in there because the molar mass of ammonia did not change since we started this problem. And then I need the molar mass of nitrogen. That's going to be 2 times 14.01. 2 times 14.01, which is 28.02 grams of nitrogen is equal to 1 mole of nitrogen. So 1 mole is 28.02 grams. 25.2 times 1 divided by 28.02 times 2 times 17.034 equals 30.639 grams of ammonia. And again, that would have 3 significant figures. The next question you ask yourself is, which of those numbers is smaller? Well, the 30 is smaller, right? This guy. That didn't work so well. So, what's the maximum amount of ammonia that can be made? It's 30.6 grams of ammonia. Do not be thrown off by this word maximum and think, oh, I need to choose the larger number. That number is larger. But you can't make that much ammonia if this is all the nitrogen you have, because you're going to run out. If you're making cars and you run out of wheels, can you keep making cars? No. It's not a car if it doesn't have wheels. You have to have all the pieces. Any questions? Yes?
So for hydrogen for the gram, when you calculate it together, you use 1.008. What did you use 1.01?
That's a good question. I used 1.008 because that's what the periodic table in my head says. It's also, I think, well, anyway, I've seen it other places too. Just I didn't make it up. If the periodic table you're using says 1.01, you should use that. If it says 1.00797, you should use that. I'm rounding to 4 significant figures in the masses just for convenience, because everywhere I go, the periodic tables are a little different. Because the one up there is 1.00794, and the one on the other side of the classroom is 1.0079, right? It shouldn't matter. In fact, let's calculate this. 8.42 divided by 2.02 instead, times 2 divided by 3 times 17.034. It comes out to 47.3 grams. So it made a difference in the last digit, the uncertain digit. If there's a difference of 1 or 2 there, it's nothing to worry about. And that's a good thing to remember on an exam. So if you came up with, let's just get a new sheet of paper here. Well, that didn't work. That works. Okay. So if you came up with 47.4 grams as your answer, and the choices were 47.3 grams and 94.88 grams, and I'll just stop at 3 because I'm tired of making up numbers. Oh, and let's put in this one. I hate this one. None of the above. Don't you hate that? That'll make you second guess yourself. The correct answer is A. your answer differs a little bit in the last digit. That can happen when you round intermediate values, if you're using a periodic table that's slightly different, but that does not mean that this is an incorrect answer. So you should not choose none of the above in this situation, because this is extremely close to that. It's close enough. And I know that's an idea that is disturbing to students. If something like this were to come up in an exam, and you're just like, I don't know what to do, I don't know what to do, do the rest of the exam, and when you come to turn in the exam, you can ask me about it, because I don't want to trick you with something like this and have you choose D and get it wrong, okay? So that's a very good question. Any other questions? Let's see. So we did that one. Let's do this one. This reaction can be used to obtain iron from iron ore. The reaction of 185 grams of Fe2O3 with 93.5 grams of CO produces 87.4 grams of Fe. Find the limiting reactant, theoretical yield, and percent yield. Okay. This one's a little different too. Well, again, let's use the balanced chemical equation to organize the information. So I have 185 grams of that, and I have 95.3 grams of this, and it says I've got 87.4 grams of iron. And now what? I have to figure out, well, what is it asking me? It wants the limiting reactant, okay, that'll come later, the theoretical yield. But they gave me this. Is this the theoretical yield? No. This reaction produces this amount. This is the actual yield. They always have to give you the actual yield in a problem like this. In lab, when you're doing an experiment, it's the thing you measure at the end. But in this classroom, they have to give it to you. So this is the actual yield. The reaction of this much Fe2O3 and that much CO produces that much iron. They want us to calculate or find the theoretical yield. So I'm going to put question mark grams. I have to calculate that. And we've done several of these now. I'm going to take the mass of this and figure out what mass of that. I'm going to take the mass of the other reactant and figure out the mass of iron. And the smaller one is the theoretical yield. Ready? Should we have a race? Now, try to do this on your paper while I do it on the screen. So 185 grams of Fe2O3. Grams to moles to moles to grams. So grams of that to moles of that. To moles of what I'm trying to find, which is the Fe, to grams of Fe. And this time I'm writing bigger for some reason and it's not fitting very well. Grams of Fe2O3 down there. So those cancel out. And I need moles of Fe2O3. So those cancel out. And I need moles of Fe down here. So those cancel out. In front of Fe, there's a 2. So in my mole ratio, I put a 2 in front of Fe. In front of Fe2O3, there's nothing. So I put a 1. I could leave it blank, but I don't feel like it. I'm going to do the last one first because it's the easiest. Iron is 55.85. grams per mole. And then I need the molar mass of Fe2O3. So it's got 2 irons, doing this up at the top. So 2 times 55.85. Yeah. Plus 3 oxygens. Uh, 159.7. So 1 mole of Fe2O3 weighs 159.7 grams. And so I'm going to sneak the answer in here. Got 185 divided by 159.7 times 2 times 55.85. Bless you. 129 I was going to call it 0.4 grams. It's got 3 significant figures. Now I have to do it again with the different reactant, the CO. 95.3 grams of carbon monoxide. Oh, I'm going to have to slant down because otherwise I'm going to run into my other answer. Grams to moles. To moles to grams. The units cancel out. Those units are going to cancel out. And these units are going to cancel out. Be careful with the sizes of your letters. That's a capital O. Don't copy it down too small and start using the molar mass of cobalt, which is capital C, little o. I like the middle one first. 2 irons and 3 COs. The last one's easy too, 55.85. It's the same as the one above it. Then I need carbon monoxide, which is the molar mass of carbon. There's 1 of those, and there's 1 oxygen, and so that ends up being 28.01. 28.01 grams. So I've got 95.3 divided by 28.01 times 2 divided by 3 times 55.85, and that comes out to be 126.7 grams. If I use up all the iron 3 oxide, I make 129 grams. If I use up all the carbon monoxide, I can make 126.7 grams. So what's my theoretical yield? 126. It's this one. So that's my theoretical yield. Let's do a different color here for our answers. Theoretical yield equals 127 grams of iron. That is a final answer, so I'm going to round and use the correct number of significant figures. What is the limiting reactant? It's the carbon monoxide, the CO. Limiting reactant is the carbon monoxide. Because if we take this and trace it back to see what started all of that, it was the CO. What else do we need to find? The percent yield. So I'm going to create space. Do you remember what the equation for percent yield is? Actual over theoretical. So percent yield is the actual over the theoretical times 100. We just calculated the theoretical. Since I'm using it in a calculation, I'm going to revert to this one instead of using the rounded. It's better. So that many grams. What's the actual yield? The 87.4 that they gave us. 87.4 grams and times 100. So 87.4 divided by 126.7 times 100. And how many significant figures should this percent have? Should have 3. So it is 68.98%. When I round that, it rounds up to 69.0%. And that's the percent yield. Questions? If you want to have copies of these slides on your phone, the best way to do that is to go to YouTube and scroll through the video till you get to this slide, pause it, and do a screenshot, and then you've got a beautiful picture. So no questions. Awesome.